Hi, my name is Zofia Stanley. I'm a research scientist at Ceres and NOAA Physical Sciences Laboratory in Boulder, Colorado. I want to first of all thank the organizers for putting together this session on ocean data assimilation and for allowing me to give this presentation. Unfortunately, I'm not able to be here today, but I'd be very, very happy to take any of your questions either on the YoPad or on the last slide of this presentation. I will put up my email address and I'd be happy to answer any questions by email. So today I want to talk a bit about actually coupled data assimilation. So coupled atmosphere-ocean data assimilation is what I'm going to be talking about. And specifically, I want to talk about strongly coupled data assimilation and vertical localization for strongly coupled data assimilation. So just so that we're all on the same page when we're talking about coupled data assimilation, I'm thinking about sort of two different paradigms of coupled data assimilation. The first is what we would call weakly coupled data assimilation, where observations of the atmosphere are allowed to update the atmospheric model state, and likewise observations of the ocean are allowed to update the ocean model state. Again, this is weakly coupled data assimilation, which is contrasted with what we would call strongly coupled data assimilation, where observations of the atmosphere are allowed to update the ocean model state and vice versa. Now, there are all sorts of sort of intermediate schemes and methods that don't necessarily fall neatly into weakly or strongly coupled data assimilation, like outer loop coupling, etc. I'm not going to be talking about those today. I'm just really going to be focusing on these sort of two extremes of weakly coupled or strongly coupled data assimilation. And the reason that I'm looking at strongly coupled data assimilation and interested in strongly coupled data assimilation is that there are a few sort of physical reasons why we think that strongly coupled data assimilation might be beneficial. First of all, cross-fluid correlations do exist in the real world. We know that there are air-sea interactions, strong air-sea interactions in certain regimes, and those we may be able to sort of capitalize on those correlations and benefit the data assimilation scheme. Secondly, if we have a strongly coupled data assimilation scheme in place, we may be better able to utilize satellite observations, which are highly sensitive to both fluids. So in this work, in this presentation, what I'm going to talk about is a study that we've done on looking at different types of vertical localization using vertical columns from a global weakly coupled cycling system. So the data set, the model output rather, that I'm using is forecasts from NOAA's Unified Forecast System, a research to operations project. And this data set was produced by two of my colleagues, Henry and Wei, at a nominal 1 degree resolution using a weakly coupled cycling system with an 80-member ensemble. And what I want to sort of focus on here are just the correlations in temperature between sea surface temperature and in the ocean and 2 meter temperature in the atmosphere. So that's what we'll start looking at. That's what this map is of. And what you can see is that these correlations are sort of weak in an average sense. 90% of the correlations that we're seeing are less than 0.3. However, in certain regions, there are much larger correlations, and those larger correlations of sort of 0.4, 0.5, those are the ones that we're really sort of hoping to capitalize on when we're thinking about strongly coupled data assimilation. So because I am looking at vertical columns, I'll also put up a plot of vertical correlations. And so here I'm plotting the correlation between sea surface temperature and temperature columns in the atmosphere and the ocean. And so if you look at the correlation between sea surface temperature and temperature in the ocean, we can see that, it's perfectly correlated with itself, and then strongly correlated through the mixed layer, and then kind of drops to zero as we're looking at correlations between sea surface temperature and sort of deeper ocean temperatures. In the atmosphere, the story is quite different. So the correlation between sea surface temperature and the lowest atmospheric level temperature in that level, which I'll call atmospheric surface temperature, already is much smaller. So again, these correlations that we're seeing here are, sort of 0.3 or maybe even less, maybe even smaller than 0.3. And then they're a bit noisier in the atmosphere, and we don't think that's necessarily indicative of sort of real-world conditions. It might just sort of be model error, model noise that we're seeing here. However, what is certainly true is that these correlations are definitely much smaller as soon as you cross that fluid interface. And that's a real challenge for strongly coupled data assimilation, and one that we're sort of hoping to address with a reasonable localization scheme. So we've looked at 3 different localization schemes, and these are all, in some sense, designed to be optimal. And we'll get into what that sort of means as we talk through each one of them. But the first scheme that I looked at is the best we could possibly hope to do. I'll back up a bit here. I'm looking at the error metrics that I'm using here to determine, what's optimal is an error in the Kalman gain. And I'm looking at specifically R matrix localization, so inflating those observation errors when the state that we're updating is far away from the observation that we have. So the first localization scheme that I looked at is what we're calling empirical optimal R localization, EORL. If you've read Tobias's recent paper on empirical optimal localization, you might recognize this. So this is heavily inspired by his work. However, he was looking at B matrix localization, and we're looking at R matrix localization. So that's where that EORL comes in. That R is for R matrix localization. And basically what this is at every level of the atmosphere and then the ocean, we're just setting the optimal localization weight for that level. So there's no parametric form enforced here, no sort of regularity or anything that we're enforcing. It's just at every level we're looking at sort of the optimal weight for that level. And you can see that this is quite noisy. So if you look on the plots shown here, that EORL is in that red dashed line. And again, I'm looking at temperature in the atmosphere and the ocean, and then I'm looking at 2 different observation types. So looking at first observing atmospheric surface temperature and then also observing sea surface temperature, and that's the difference between those 2 plots there. The other localization strategies that we looked at are parametric. So the first is just simply taking the Gasparian cone commonly used localization function and setting an optimal localization radius in both the atmosphere and the ocean for each observation type. And then you can also allow the height of that Gaspari cone localization function to shift. So for option 2, the height is just set to be 1. For option 3, that height is allowed to vary, and we do also estimate the best sort of height for that function. We're calling that an attenuation factor. So those 2 Gaspari cone options are shown here with solid lines. The darker one is just the Gaspari cone with the height fixed to be 1, and the lighter blue color is that Gaspari cone with the attenuation factor. The reason we thought the attenuation factor might be a good idea is because, as we saw in the previous slide with the vertical columns of the vertical correlations, you see that the correlation drops as soon as you cross that fluid interface, and so we thought that having a localization function with the height, with a smaller height might also be advantageous in this coupled setup. So these are the 3 optimal localization strategies that we're looking at, and I will show you errors on the next slide, except that I'm not actually going to show error. I'm going to show % improvement over persistence. So I'm not working in a cycling system here. I'm just working with a single update. So for me, persistence means no change between the background state and the analysis. So the analysis is just equal to the background state. That's persistence for me. So this improvement over persistence that we're looking at here is our data assimilation step making an improvement to the state estimate. I'm showing this percent improvement over persistence as a violin plot. If you've never seen a violin plot before, this is just another way of looking at a distribution. So if you take a single one of these sort of violin plots, you chop it in half and you flip it on its side, that's a distribution. And so that's how I'm showing these. So the wider these violin plots are, the more sort of density we have at that value. So if we look here, there are sort of two very different stories to be told here. So for example, first, when we assimilate atmospheric surface temperature into the atmosphere or sea surface temperature into the ocean, both of those are within fluid assimilation steps, we see that it doesn't really matter which localization scheme we use. All three of them are doing quite well and giving us a large improvement over persistence. On the other hand, when we then look at those sort of off-diagonal plots, the ones that I'm showing in blue here, these are the cross-fluid assimilation, so assimilation of, for example, sea surface temperature into the atmosphere. The story is quite different. Here, it really does matter which localization scheme you use, and only the very best, so the EORL, empirical optimal, our localization, is consistently giving us an improvement over persistence across the entire globe and all of the columns that we looked at. The other two, the Gaspari cone-based parametric forms, we see quite a bit, a lot of the time, there's simply no improvement over persistence. And I want to point out here that persistence for these off-diagonal terms is the same as weakly coupled data assimilation. Because in weakly coupled data assimilation, sea surface temperature is not allowed to update the atmospheric state. So that's simply persistence, basically, here. So when we're saying that there's no improvement over persistence, we're also saying there's no improvement for strongly coupled data assimilation over weakly coupled data assimilation at that particular grid cell with this particular model, and this many ensemble members, right? And so that's a good segue into the number of ensemble members that we used here. So this data is, the correlations are computed from an 80-member ensemble, but then we take sort of neighborhoods around each vertical column and use those to compute what we think are sort of more robust true correlations. From those true correlations, we then sample smaller ensemble sizes. So we think that true correlation is sort of it has a nominal ensemble size of somewhere around 250, maybe 300 is what we might expect for this sort of large ensemble that we're using that we've sort of bootstrapped together to estimate these true correlations. From that, we're then drawing smaller ensembles. So here we've drawn ensembles of 80 members. And this, we do across the globe and 1,000 times at each grid cell. We then also wanted to look at sort of how does the story change if we draw a larger ensemble. So we're going to bump this ensemble size up to 240 and then repeat the process. So again, we're seeing that for the within fluid assimilation, it really doesn't matter which localization scheme you pick. That's what we would expect, given that it doesn't matter with an 80-member ensemble, it shouldn't matter with the 240-member ensemble. Really what's interesting here is this cross-fluid assimilation. And here we're seeing that there is a difference if we're able to draw, if we have a larger ensemble, then certainly with this optimal localization, we're doing better than persistence. So strongly coupled data assimilation is better than weakly coupled data assimilation almost always. But again, that's in this very specialized case where we are able to pick the absolute best localization weights at each vertical level. If we turn our attention to the Gaspari cone, these parametric forms, we see that there's still certainly some times when strongly coupled data assimilation does not show an improvement over weakly coupled data assimilation, but that's less often the case with this larger ensemble size, and we are getting sort of more of the time we are seeing an improvement for strongly coupled data assimilation over weakly coupled data assimilation. So we wanted to, the last thing I'll talk about, the last thing I'll show you is we wanted to look at the effect of this ensemble size on these different localization schemes. And so that's what I'm showing here. It's the same for subplots that we've been looking at. So these two different observation types of atmospheric surface temperature and sea surface temperature, and the two different fluids, atmosphere and ocean. But now I'm just showing, I'm showing three localization schemes, but they're slightly different. So I'm still showing empirical optimal R localization, and I'm still showing Gaspari cone. I've dropped the Gaspari cone with the attenuation factor because we didn't see too much of a difference there between those two. And then I'm also showing no localization. So no localization is in this red dashed dot line, Gaspari cone, the light blue dashed line, and empirical optimal R localization is this dark blue line. And we see that, as we expect, empirical optimal always does the best, followed by Gaspari cone, followed by no localization. The other thing that is shown on these all four of these plots is a sort of operational ensemble size. So, for example, GEFS that NOAA uses has an 80-member ensemble, and that's shown in that dashed black line there. And so what we see at the operational ensemble size with both of the within fluid assimilation is that it doesn't really matter too much what localization scheme you use. That's consistent with what we've seen before. However, for strongly coupled data assimilation, certainly what we see is that at this operational ensemble size, we definitely need to use localization. That's not a surprise. What is perhaps surprising is that even with the very best Gaspari cone localization, where we pick the optimal localization radius at every single grid point, it's still not giving us a whole lot of improvement over persistence. Again, that's consistent with what we saw before, but even out to 240, 250 ensemble members, we're still not seeing a huge improvement, and even with the very best localization scheme, it's still not a giant improvement. And so what we've sort of learned from this, our outlook, is that certainly there is more work needed on strongly coupled data assimilation. There are certainly situations where we've seen advantages for strongly coupled data assimilation over weakly coupled data assimilation, and that's consistent with previous literature as well. However, in order to actually realize these gains in a operational system, in a real world, global system, we're going to need to do some work. Some options for what we could do include increasing ensemble size, but that's expensive, and even increasing it by a factor of 3 up to 240 ensemble members from 80 ensemble members is going to give us some gains, but not maybe as much as we might hope for. Alternatively, we could improve our localization schemes. That's sort of what this work was looking into, but it's not exactly clear how that would work. We would maybe even need to start thinking sort of new ways of incorporating localization into our data assimilation system. Finally, another option is to start looking at improving estimates of correlation without increasing the ensemble size. There's already been some work done on this in lower dimensional systems, and we're thinking about this now also in high dimensional systems as well, of just directly learning correlations using sort of a machine learning technique, for example. With that, I'll end, and again, I highly encourage you to send me any questions that you might have by email. Thank you all very much for listening, and yeah, I hope to correspond with some of you in the future.